yesterday about chapter 7 homework due date being delayed. That was just because everybody was still working very hard on it here in class. So feel free to stay after today and get, whatever questions you have answered, work on it again over the weekend, try to finish it up. And if there's any remaining questions, we can talk about those on Monday. You are continuing doing some reading that, again, is just processing the idea, putting together the relativity of simultaneity, length contraction, and time dilation, and how it can all make sense together, and sort of presenting what doubts someone might have and then relieving those doubts as best he can at this time. So keep up with the reading and the posting. And I'm not going to address any of those posts today, but I certainly will early next week on the stuff that you read for today and also the stuff that you're supposed to read either for by Sunday night or Monday night. Can't remember. All right. So we're going to take a detour today into some ideas that are associated with, we've been talking about the special theory of relativity, and that's, sort of applicable to regions of space and space-time where there's no sizable gravitational forces, or we can incorporate gravity in the same way we incorporate other forces. We'll talk about that later. But now we're going to dabble a little bit in general relativity, which is Einstein's later and, of course, more general work that incorporates special relativity into it, but more. It also incorporates gravity as an integral part of it, and we conceive of gravity as being something different. It's not an ordinary force. In fact, all of its effects come from the fact that space-time is something that we're going to conceive of as a curved shape. It has some curvature to it. And so even though things seem like they're subject to a force when they're under the influence of gravity, in fact, they're following the most natural paths possible in space-time. But this takes a little bit of effort to build up. I don't think I'm going to have any homework associated with this. If there are some major takeaways I want you to know, I will state those at the end of this material, what it is that I really want you to remember. But for the most part, just let it kind of wash over you. I'm hoping it's fun. It's sort of visual. There's very little calculation that we're doing, essentially almost no calculation. It's developing intuition about curved spaces and how that relates to things. But there are several pieces that have to be put together. So here's a little outline of what we're going to do over the next couple of days of class, stuff that's not talked about in Mermin. Well, actually, number 1 is talked about Mermin. I think it's in chapter 17. And I do hope that maybe that's something that we get to by the end, because we won't be talking about everything that's in that chapter now, although I may allude to a few things. So we're going to talk about how to visualize motion through space and in time in a diagram on a page. Those are called space-time diagrams with a little bit of extra structure. You would call that a Minkowski diagram. So that's a term that we'll be using later on, assuming we have enough time to get there. Then we're going to need some details, because general relativity is a theory of gravity. We need to know a little bit about how gravity behaves. And since this is not an ordinary physics class, we need to sort of do that from the ground up. So we're going to talk about how Newton describes motions, Newton's 3 laws of motion, very, very briefly, just the bare minimums that we need. And Newton's law of gravity, where we conceive of it as an ordinary force that causes things to accelerate. Then we're going to introduce the idea of curvature. And because curved space-time is a little bit abstract, we're first going to start talking about just curved space. What if we lived in just a static space? We don't worry about time, but just think about space itself as being curved. How would that manifest itself in experiments, or in marching around through space? How would we see the curvature of space manifested, and understanding different kinds of curvature that we can visualize? And then finally, connecting that to general relativity, which is the idea that space itself is not just curved, but space and time together are curved. And we'll find out that, we're already seeing clues that you can't really think of space as a thing by itself, like Newton thinks of space as just a big container. Rather, space and time are really entwined with each other because things that happen simultaneously, but spread out from one person's point of view, are not simultaneous in another point of view. So things that are just purely spatially related to each other from one person's point of view are staggered in time from another person's point of view. So space and time are kind of entwined in relativity. They maintain that sense of being entwined in general relativity. Okay, and so we want to find out how curved space-time essentially can do the work of a gravitational force. The real theory of general relativity has a lot of highfalutin math in it. It's really hard to understand. So we're not going to really go into the math, but I want you to come away with a qualitative idea about how curved space-time can mimic gravitational kinds of effects, makes things seem like they're moving. Well, they actually are moving toward each other, but there's no force in the traditional sense. And then finally, some things that might connect with some of the ideas that get developed for, time travel and things like that in the philosophy course. The idea of the universe is expanding, or the expansion of space itself, the Big Bang and the Big Crunch, how to envision those in terms of curved space-time, what it would mean, at least qualitatively, to travel backward in time, although nobody knows how to do that, and what the idea of a wormhole is. All of these were ideas that came up the last time we did these courses together, and so I thought we better just at least draw some pictures of them or show pictures that other people have drawn for them. So let's start off with just talking about diagrams. We got to take these things one at a time. It'll take a couple of days to get through all of this. So we're going to draw a picture of the motion of people through time. Now, because we want to draw them on a two-dimensional page, we're going to imagine these people or objects that are moving around are only moving on the x-axis. So they really are living essentially in one dimension. Someone is just going to move back and forth on the x-axis the same way that Alice was running along one dimension and going from home to the deli in those homework problems, okay? So here's our x-axis. I've got it labeled with tick marks and units and numbers on there. And we're going to draw it from the point of view of the motion that people are undergoing from a certain IRF. So I'm going to call that inertial reference frame just F. The picture, we'll find out, is going to look different if we switch to different IRFs. But from a certain point of view, here's what's seen as described by someone in F. One day, Alice slowly sneaks up on Bob, who's standing still initially. When she reaches him, he's surprised, and he runs away quickly while she stands still laughing. Okay, this is the description. Of course, standing still is something that's particular to a certain inertial reference frame, but we're going to draw it in that particular way. So let's add a time axis perpendicular. And what I want to draw is, at any given time, what are the positions of Alice and Bob qualitatively here? I didn't really give any real details, but just something that qualitatively agrees with this. And so what I've got here with an x-axis and a t-axis, and we're going to start drawing the motion of objects in it, we call that a space-time diagram because it includes both space and time, of course. Okay? So here's something that agrees with that. I'm showing Alice in red and Bob in green there. Okay? So here's Bob initially standing at rest. When you stand at rest, that means as time goes on, your x-coordinate doesn't change. Everybody agree with that initial part, that as t increases, that means we're going up the page. And traditionally in relativity, for whatever reason, people like to draw time as going upwards. That's just the way everyone does it in relativity. Notice x isn't changing. Bob is standing on the x-axis at 2.5 meters, and it's staying at 2.5 meters here. Whereas Alice's x-coordinate is slowly increasing as she creeps up on Bob. As time increases, her x-coordinate is increasing. And then finally, she reaches Bob at this particular time. That's 2 seconds on my diagram, right? And at that point, she startles Bob. Bob runs off at a great rate, or really quickly. And notice that the quickness of him, how fast he's going, is given by the slope of this line. In other words, the more it's tilted away from the vertical, a vertical line corresponds to standing still. If it's tilted a little bit, that means you're moving slowly. The more it's tilted, the faster you're going, because in a certain amount of time, if you go over by a lot, that means you're moving really quickly. Okay, so highly tilted lines that are tilted away from the vertical are people or objects that are moving really fast. Okay, and here's Alice. She's later standing still laughing in this period. So that kind of matches the description roughly there. Okay. So to give a little extra terminology, we're going to talk about lines that are followed by localized objects like a person or a spaceship that's traveling or a planet. Even on these diagrams, a planet might be drawn as like a point-like object that's moving up. If we're traveling light years away, a planet's pretty small. We call those lines. They're not really lines, they're curves, right? They could be even curved. These happen to be piecewise linear, but they're called world lines just because they're one-dimensional curves. Okay, so Alice has her world line, Bob has his world line, and whenever you see a world line that is vertical, that means someone's at rest, at least as seen in the inertial reference frame that you're drawing the diagram for. Okay, so we're developing a geometric picture of not just what is the state of affairs at one moment in time, but the whole history of a state of affairs, right? This is a lot of events that are happening here, not just a single event or a single location of everything at one time. Okay, so we can see Alice moving slowly. That's small tilt away from the vertical. Bob being at rest, that's actually being a vertical line segment in that period of time, and then Bob moving quickly is tilted over more. To practice with this, we're going to do a worksheet. And for those of you who are on Zoom, I really literally just hit send on the email because I forgot to send it from my office right as class was starting. So check your email. You should have an attachment for today. And we're going to draw a space-time diagram for someone going to a distant planet on a spaceship, staying there for a while, and then traveling back to Earth. I only want you to do parts A through D. We'll do E in just a bit. And to help you with this, because we're going to find out that things are traveling along line segments, I brought some rulers just to help you draw straight lines, although it wouldn't be the end of the world if your straight line were a little bit crumpled. So if you're at home, take out a ruler. I'll pass out some here in class. The axes are not labeled on there, so one nice thing about having a ruler is if you want to make equally spaced tick marks, the description on this problem, the period of time that you're supposed to draw the events for, encompass 11 years. I think there's 5 years of, I can't remember exactly what it is, but 6 years on the way out and then 4 years on the way back, and they stay at the planet for a year. So that adds up to 11 years. So you need 11 years, an 11-year distance on the vertical axis. I size the axis so that if you use the centimeter marking on here, 11 centimeters will fit nicely if you start down on the x-axis and go up from there. So I would use centimeter tick marks on the vertical axis, and you're also supposed to use them on the horizontal axis. So here, we've got planet X is 3 light years from Earth. Both are in the same inertial reference frame. At time t equals 0, Earthlings send a spaceship toward X at half of c. When the spaceship arrives at X, it stays there for 1 year and then returns directly to Earth at a greater speed, 3/4 of c. First, a little calculation. How long does it take, according to the Earth IRF, for the trip to X take, and then how long does it take on the way back? That's just to help you scale things on your diagram. You should get 6 years and then 4 years because they're going faster on the way back. And so you're supposed to draw their world line of the ship from the point of view of the frame where Earth is at the origin. So Earth has a vertical world line just going up along the t-axis there, right? What does the ship's world line look like? How far out does it go? Where does it turn around? And then you're also supposed to, in D, add another world line for a light pulse. So I'm going to put those of you on Zoom into a breakout room, and I'll come check on you in just a minute. Meanwhile, I'm going to draw my axes on the board as best I can. Don't understand why this camera has so much trouble auto-focusing. Is it the right light reflection, maybe? So strange. try closing this, maybe. Weird. We're not moving enough, I guess. Why is it not able to autofocus on this? It's trying to autofocus and nothing is in focus. That's really weird. I know we've had this problem before. Seems okay maybe when it's closer. All right, I'm going to check in with the breakout room and maybe call them back. Maybe I'll just close it and have them come back. I closed the breakout room just so that we could all have a conversation together. I've spent all the time fiddling around with this camera because I can't seem to get it to autofocus, but it seems okay now, even though it's a little distorted, now that I moved it up close to the board, which is not ideal, but hopefully it shows what we need to see. Okay, so let's just go through the worksheet step by step. Let me just ask a question. I guess we should go through A and B together, at least A, because B is kind of the same thing. How do I calculate how long the trip takes in the Earth inertial reference frame? And the answer is, well, we've got the speed the person's going at in the Earth frame, and we've got the distance they have to go, which is 3 light years. And so we can calculate the time it takes to get out there. So to answer A, and B is very similar. I'm going to erase this in just a second. But to answer A, we would say using distance equals speed times time, right? The distance we have to go is 3 light years. And I always write a light year when I'm doing distance equals speed times time as 1 light year is the speed light travels at, c, times the amount of time it travels, 1 year. So a light year can be equivalently written as c times 1 year. That's just a different unit for a light year that uses distance equals speed times time. Okay, that's how far the ship had to go. It's going on the way out at 0.5 c. And we're interested in that time that it takes. And of course, the benefit of writing a light year this way is I can just cancel out that c. I never have to put in a 3 times 10 to the 8th anywhere. And so it looks like I've got 3 years over here. I've got to divide by 0.5. When you divide by 0.5, you multiply by 2. So t is going to be 6 years in A. And similarly in B, the only thing that changes is this goes to 3/4 or 0.75. That gives us 4 years. It takes less time if you're going faster. So the answer to B is 4 years, same kind of calculation. Questions on those two? Okay. Straightforward enough, I hope, at this point. So let me erase this because it's in the middle of my diagram. And now we've got to draw this trip. We're supposed to take Earth to be at the origin, and this is drawn from the inertial reference frame point of view where Earth is at rest. So if Earth starts out over here at the origin, the Earth world line is going to be right on top of the t-axis. So Earth is here. It's hard to draw that in here, but I'm just sort of darkening in the time axis. That's Earth right there. And what about the spaceship? Well, how about the X world line? Let's see. X is at 3 light years, right? So here's 3 light years away. I had you draw these tick marks, or at least if you read the instructions carefully, they were supposed to be equal. That looks a little bit funny here, but it'll make sense later on in the course when we do more with this. We'll always make these tick marks equal like this when we're using years and light years. So here's the X world line. X is at rest with respect to Earth, and therefore its world line is vertical too in that same reference frame. It's sitting still from the point of view of that reference frame. Now, what is the ship doing? Well, we know the ship starts out at Earth at time t equals 0. It ends up at X, and it takes 6 years to get there. And since it's going at a constant speed the whole time, you know, this requires a thought, but that means that the world line is going to be a straight line between there. Because in 1 year, it goes over a certain distance. In the next year, it goes over the same distance. The next year, it goes over the same distance. That's saying it has a constant slope, right? If it has a constant slope, we're talking about a line segment. So here it is at 6 years. Then they wait on X for a year, so they sit still there. And then they come back to Earth, but they sort of hightail it back to Earth. They come back to Earth, we found out in part B, in only 4 years. So 4 years later, 1, 2, 3, 4, they're back here at Earth. So I've got to connect these 2 points. And that is the world line corresponding to the spaceship. It's got a linear part, then a vertical linear part, then another linear part that has a larger tip with respect to the vertical on the upper part than the lower part. Okay, that's A, B, and C. Questions on those? And then in D, D says, at a world line for a light pulse that is emitted from X toward Earth, that means it's going to start here and head up towards Earth. At the same moment, it's supposed to say in the Earth IRF, the ship was launched from Earth. So here we are picturing in the Earth IRF, here's a particular moment at time t equals 0 when the ship was launched. So here's that same moment. That light pulse is emitted there. The only question is, what tilt should I give it? Can anybody figure out what angle or where I should head up to on this axis for a light pulse? In other words, in how long does it take to go 3 light years for a light pulse? It takes 3 years, right? Because light pulses travel 1 light year in every year. So that's why this is kind of convenient. So 3 light years distance takes 3 years. And so light pulses are always, we're going to find out, when we scale our axes this way. And by scale our axes, I mean when we do x in light years and t in years, light pulses will always travel on these 45-degree lines that have a slope of 1 or -1, depending on which way they're traveling. In any case, that's not particularly important for us, but there's the light pulse world line shown down at the bottom. Questions on that? Let's just practice thinking about space-time diagrams.
So could I ask a question?
Absolutely.
Okay, so I think I was confused earlier because I got all the right slopes, but I kept pointing them away from the Earth, the Earth world line. So
You mean the x-axis?
so no, I mean, so for the y-axis, right, which is the Earth world line. Like for instance, when I did the light pulse, I started from 0, 0, and I took it to 3, 3.
Yes.
But I went in the other direction. Like I didn't do 0, 3 to 0, 3. I went from 0, 0 to 3, 3.
Yes.
Because I was not intersecting the light pulse with the Earth world line, and similarly up at the top. So
yes. So
any suggestions of how to think about thinking in terms of when things intersect or how things intersect? I think that's where I kind of like kept drawing things, but not really thinking that in fact the light pulse is being seen from Earth, or that the ship is returning to Earth so that those world lines are supposed to connect again.
yeah.
Does that make sense?
So we see at some point, interestingly, the light pulse passes the path of the ship, so they might be able to intercept a little bit of that light pulse and see it as it's traveling. Whereas in your way of drawing it, they never would have intersected as it went up here, right?
Yeah.
The key in the description is that the light pulse was sent from X at that earlier time, and X is here. And then it was sent toward Earth, so it's heading over towards the Earth world line. It should reach there at a later time. So that there's definitely, it has to go this way. It can't go this way. This would be a light pulse sent from Earth towards X at the same time the ship was launched. But we're told at the same time, according to Earthlings, the ship was launched, and this is the Earth point of view we're drawing here. At the same time, that's over here, a light pulse originates from X and ends up at Earth. So it's in those words. Is that helping?
Yes, it does. You know what? I didn't even think of putting I did not do the world line for Planet X. So that, I think that would have helped just me reading more carefully.
Yes, maybe, and even label it with an X or something like that. In my solution, I also didn't draw the world line for X. It wasn't asked for in here, but it certainly helps. You didn't also have to draw the world line for Earth, but having them in there sometimes gives you a good reference point so that you don't get them mixed up. All right, good. Any other questions? That's not supposed to be a complicated exercise, but rather something to make us just practice in this simple context with how to draw these kinds of things, because, you know, when you look at that diagram that we just created, it doesn't necessarily look like something traveling somewhere and coming back. It's a little bit abstract. Okay, let me turn the lights off again here and adjust something so that we can see the whole screen here. Okay, so somehow I'm not in control of this either. Let's do this. Good, okay. Now, important thing to realize is that there's nothing particularly Einsteinian about this. Newton would, if he chose to draw these events the same way, he would draw the same exact picture. So there's nothing that involves relativity yet, you know, other than the fact that we drew a light pulse that happened to be going at c. Newton would not have known anything about that. Now, the principle of relativity tells us there's no fundamental truth to the statement that B starts out at rest. That was just a biased point of view from the point of view of Bob starting out, or, you know, from the point of view of someone at rest with respect to Earth. So we might ask ourselves, how would the space-time diagram be drawn from a different frame's perspective. This is just from a frame that's sitting at rest with respect to Earth. But maybe we want to draw the frame of someone who's initially moving along with Alice. And to gain intuition, at least first, we're going to draw how Newton would think about how to change this over to that other point of view. And instead of, we could draw a totally different diagram where we reorient, if we wanted to take a point of view of someone who's moving along with Alice, that IRF point of view, we could redraw that point of view vertically, and we'll do some of that later on in the course. But for right now, what I'm going to do is just use the same diagram but draw a different axis on there. So here's the same set of world lines. It was viewed from IRF F, and its corresponding axes are called X and T. I've drawn them in blue there, so they match up with the label. I'm now going to add a second set of axes on there. We'll call it IRF F prime, and we can just put them on the same diagram, and that F prime is going to be a different inertial reference frame, one that's moving along with the same velocity or same speed and direction that Alice is moving originally. So notice the tip of this T prime line is the same as the the tilt of the T line is the same as the tilt of Alice's line initially. Now, how do I use those axes? The X prime axis is down here right next to the X axis, and from Newton's point of view, we would just keep that the same like that. And to figure out where in IRF F prime these events occur, what we do is say, okay, to find out what the coordinates of this crossing point are right here, where A crosses B, what we do is say, well, let's see, to read the X prime axis, I just go straight down. That looks like about 2.5 down there on the X prime axis. That's sort of shown in a yellow color. And I just go to find the T prime. I'm sorry, I'm misspeaking there. So let me start over. To find the coordinates of this particular point where A and B cross right there, what we do is, starting at the origin, first go parallel to the T prime axis, in other words, for the point of view we want to take. So this is the point of view of an inertial reference frame that's moving along with Alice initially. And we would say the coordinates of this, we need to stop at the point where we get up to the same height as that point. And then we go over to here. And so we would say this occurs at time T prime equals 2 and X prime equals, we have to go back along here. So in other words, I guess what I'm trying to say in a complicated way is, just like to find the coordinates of this on the blue axes, what we do is go along the edges of a rectangle and see how far do we go horizontally and how far do we go vertically. Another way to say that is go parallel to the x-axis, that gives you the x coordinate. Go parallel to the t-axis, that gives you the t coordinate. If we're using tilted axes like this, we're just going to, instead of moving along, sides of a rectangle, we're going to move along the sides of a parallelogram. First, we're going to go parallel to the x prime axis until we're at the right position, so that if we then go parallel to the t prime axis, we end up at the point we're concerned with. So that tells me that this point right up here would have coordinate t prime equals 2 seconds. That's not surprising because Newton believes in universal time. They should both agree how much time it takes, and we're doing a Newtonian point of view here. But from that point of view, this point has x coordinate, maybe 1.6 or something like that, a little bit bigger than 1.5, it looks like. Because if I follow parallel to the t-axis, this would give me where to read on there. Okay. Now, I know this is not the correct way to draw the diagram according to Einstein, because if we compare two different points of view, maybe let me just switch momentarily back to the board and draw up something on the board. Here, from the Earth point of view, or F point of view, these events, I'm going to draw some events. Every point on this diagram is an event. And these events are what we would call, from the IRF-F that we're drawing here, that has the vertical and the horizontal axes, these 4 events are simultaneous. They occur at the same time. But we already know from our work with special relativity that if they're simultaneous from the point of view of F, then relative to F prime, they should occur at different times. And if I just leave my x-axis like this and draw my new t-axis tilted like this, all of these are still going to be at the same time, because when we're trying to find the time of it, we always just go parallel to the x-axis until we hit the t-axis. So they would still be simultaneous. We're going to find out later that in addition, Einstein is going to say, in addition to tilting the t-axis when we switch to a different reference frame, we're going to have to also tilt our x-axis. And that will make, in this new frame where this is the x prime axis and this is the t prime axis, these events won't be simultaneous in the other reference frame. We're going to practice with that a lot. For right now, it's not important, but I just thought I'd mention that what we're looking at here is the Newton point of view for how to draw different axes. Okay. Let's see if I can switch back to this now. Okay. So there are a bunch of interesting events that appear on this diagram, and the events are the same events. They're publicly identifiable events, or at least the first couple I'm going to show on here. I might have called event E1 is where A collides with B. In other words, that's where Alice reaches Bob. Event E2 is where, Alice is laughing. That's the second ha in her ha-ha or something like that. That happens on Alice's world line when she's stopped and she's laughing there, right? But we said earlier on that events don't have to be publicly identifiable, all of them. Sometimes we're just going to say, hey, here's another event. It's a certain location in space and in time, and nothing important happened there. Nothing at all happened right there. But we still call it an event, even though nothing remarkable happened there. In fact, all of the points that are in this plane are considered different events in the language of Einstein, or in the language of relativity. We're not interested, maybe perhaps, in the description we're trying to build up here of the particular events of Alice and Bob here, but rather the structure of all the events that's underlying this, okay? That's what we're going to call space-time itself. And space-time in this particular drawing, it has a certain shape. It's a flat shape. It fits on a page rather nicely, but we're going to change that later. So we can think of underlying all this, there is just a plane of consisting of all the events that we might consider, and that collection of all events is space-time itself. So we don't need even those axes. That was just a particular biased point of view of space-time. Nor do we need the descriptions of any events. I can just say, hey, this blue rectangle is the collection of all space-time, in kind of the same way that Newton would say, I'm envisioning space itself as a three-dimensional container. I don't need to label anything that's happening into it. It's just this big empty container. It has all the possible locations in it. Here we have all the possible locations and times in it. And of course, it doesn't really have boundaries. It should go on forever in all the directions, but that's hard to draw. Okay? So in this way of representing things, if I do put someone's axes on here, it's always going to be true that something moving with constant velocity, and in physics, velocity means speed and direction. So constant velocity means you're going at the same speed and moving in a constant direction. We've described that as moving uniformly before too. They are going to have straight line world lines. So when I see a straight line world line going through space-time in this way of representing it, it always represents something moving uniformly, okay? Here's a particle moving at a ½ meter per second to the right, as seen in IRF F. In a different IRF, of course, it would have a different speed, but it would still be a straight line when presented in space-time. Here's a different particle zipping through space, and it happens to have a larger speed, as seen by this particular IRF. When I strip away all the details, I can say, even without the axes and without knowing anything about the inertial reference frames, just seeing that here's space-time in the way we've chosen to represent it, and here are two world lines of some objects, I know looking at those world lines, they're moving with constant velocity or moving uniformly, and that's going to be important for us to recognize. Okay. Now, in this particular case, notice I could tell which of these two was moving faster according to the IRF that we chose to draw this from by how tilted the line was. Here's just a little kind of a voting question. Someone can just shout out what they think the answer is. If ship A is moving faster than ship B according to IRF F, then is it true that ship A is also moving faster than ship B in a different IRF F prime? Yes, sometimes, or, and the sometimes means it depends on the f and the f prime. It might be or it might not be. Or is that always false, regardless of what f and f prime are? You can hold, I see Jack's holding up fingers. You can hold up fingers for 1, 2, or 3, what you're voting on. If you're on Zoom, I'm giving folks a minute to sort of digest what's being asked here. And for the symbols that are being held up, it's 2 is the clear winner, sometimes true and sometimes false. Yes, if you look at, I agree with that. That's because if I took my axes to be vertical, t is vertical and x is horizontal, yes, then this one is going to be going faster and this one slower. But we could take the point of view where my t-axis was tilted so it goes along the green line, right? And then we would say that green particle is at rest, even though, and this one certainly has some other speed, so it's going at a greater speed in that reference frame. I'm not sure why I put that point in there, but it's a good point to make. Okay, so the answer is the middle one, the second choice there. All right, that was a very brief description of how we're going to draw space-time diagrams. The takeaway is they have a certain shape. For Einstein, space-time diagrams are flat. The collection in special relativity, the collection of positions and times in the way we've agreed to draw them are going to have a flat geometry, and that's going to be important later. Now let's take a little diversion into Newton's description of gravity, because general relativity is going to incorporate gravity into it in a very natural way. And so we need to know what kind of gravity is, since again, there's no assumption that anybody's taken any physics courses. For Newton, gravity is a force. It's a force like lots of other forces, right? Forces, what do? They cause things to change their velocity, which in physics we call acceleration. So when there's a force acting on an object, if it's the only force acting on it, it will cause the object to accelerate, change its velocity. That means it might change the direction it's moving, or it might change the speed it's moving at, or it might change both, but it will cause it to deviate. And we know in terms of a space-time diagrams, that means if there's a force acting on something, it's not going to move on a straight line anymore, because a straight line means constant velocity or uniform motion. Okay, so here's a space-time diagram. I can see immediately on this diagram that the green object, at least initially, was moving with a constant velocity. It's not accelerating in this region. So for that period of time, whatever that corresponds to, it's not subject to a force. But then at this later period of time, it's definitely experiencing some force because it's not moving with constant velocity. Another word for that is acceleration. So it's accelerating in the part where it's curved. So I can see that in a space-time diagram. Now, in worksheet 1E, you're supposed to draw the world line of an object, a second ship. It says add a world line for a second spaceship, which is also launched from Earth to X at t equals 0. So it's launched from that same point at the origin, except it doesn't travel at a constant speed. It starts at rest at t equals 0, and gradually accelerates to a speed of 0.5 c when it is halfway to X. So by the time it gets out 1.5 light years away from Earth, as measured by Earthlings, it should have a speed of 0.5 c. How do I know what 0.5 c looks like on this diagram? Well, I've already got a line that has a slope corresponding to 0.5 c. That was the ship on the way out to X was traveling at 0.5 c. So it should have a slope that corresponds to the same as, I'm pointing to the board now, I'm sorry, and let me point with the camera showing there. This line of the ship on the way to X was corresponding to 0.5 c. So my ship is going to start off at rest and slowly accelerate. By the time it gets to 1.5 light years away, it should have a slope which is the same slope as that line segment. And then at that point, it starts decelerating or slowing down so that it comes to rest just as it reaches X. See if you could figure out, of course, the devil will be in the details. I don't want you to exactly do it, just qualitatively get it right. Something that isn't obviously wrong for this. it's hard to know exactly what a constant acceleration should look like on here, but we want something that at least seems to make sense. I'm not going to bother putting the Zoom folks in a breakout room since there's just one world line to draw here. So try your best to draw it on your diagram, and then we'll do it together on the camera here. Okay, let's come back together with the drawing here. I'm just going to add it on here, even though my diagram's getting to be a bit of a mess. At t equals 0, this other ship was at x equals 0 too. So it's starting off, launched at the same time, except initially it's at rest. And it starts accelerating, but initially it doesn't have any velocity. It takes a while to get up there. So which way should I leave this point just initially? Should I start going off at some angle or vertical or horizontal? What do you guys think? Just for the smallest little bit. Everett? Vertical, right. Because initially, if I'm starting off at rest, the ship is going to head upwards vertically. And I know by the time it reaches halfway out there, which is at 1.5 light years, I'm just going to draw that as a dashed line going up. The slope of its line should slowly turn over so that by the time it crosses that 1.5 light year line, it has the same slope as this one does down here. So let me try to draw that. And I know this is becoming a little bit messy. But so it's curving over like that. That means it's accelerating. And then it starts slowing down. So that means it should get closer and closer to a vertical line. So it's going to kind of snake upward in the reverse way on the way back. The point is, it's not a straight line. And I can see, therefore, that it's subject to some force. That exactly what we did there isn't so terribly important. But that's what something looks like that is accelerating. Okay. That was worksheet 1E. Once again, I need to click over here. Okay, so for Newton, gravity is a force. Forces cause things to accelerate. We now know that means it makes their world lines bend in the space-time diagrams. The gravitational force between two masses. Masses attract each other, and we don't normally recognize that in the classroom because you have to have really big masses to generate significant forces. So even though everybody is attracted to everyone else within the classroom, they're attracted to all the tables, everything doesn't crunch together in the middle of the room because the forces are so small, but they keep adding up. So when you start to get something like the moon and Earth right here, the forces can be substantial and they can actually cause things to move around in circles, like the moon moving around the Earth in a circle. That's acceleration because its velocity is changing. Even though its speed isn't changing much as it goes around, its direction is changing. Okay, so it's an attractive force. This mass exerts a force on this mass. When we say it's attractive, we mean toward it. And this mass, M, I figured out with my fancy pointer that I can't gesture too wildly or something goes wrong. I have to do it carefully and deliberately, which is against my nature. This mass, capital M, exerts a force on this mass, pulling it toward it. So that's an attractive force. So let's imagine we have two masses, and I just draw the very first parts of their world lines. In this IRF F, they're initially at rest. That's only in IRF F. If we continued their world lines long enough, they would be attracted to each other, and they would eventually run into each other. And that looks like this on the space-time diagram. So when things are a force causes those lines to bend, and in this case, they're bending toward each other. That's because it's an attractive force. Okay. There are other examples of forces, and they could do the same thing, right? We might have a negative electric charge and a positive electric charge. And if you know about electric charges, opposites attract, and so they would curve towards each other in exactly the same way, like that. Okay? Let's briefly discuss Newton's laws. We already talked about Newton's first law. In fact, it really defines what an IRF means. It means, how do you know you're viewing things from an IRF? When viewed from within an IRF, any object with no external forces on it, so you've got to put it in a context where it has no forces acting on it, you're sure there's no electric or gravitational forces, maybe you're in deep space, nothing else is around. If you're viewing it from an IRF, you will observe it move uniformly from your point of view. Because, you know, an object could just be sitting here floating in front of me, but if I start accelerating around, I'm not going to see it move uniformly from my point of view. I'd say, oh, it's going to have some crazy motion. Well, that's my fault because I'm not observing it from an IRF. So that Newton's first law defines what an inertial reference frame is, and it's only in those cases for inertial reference frames that these world lines are going to be straight for something that has no forces acting on it. All right? Super fast introduction to Newton's law. The second law tells how much something accelerates. So Newton's second law says, if an object has a mass m and it's subject to a force F, we're not really going to use this much, but those two determine the acceleration. So the greater the force, the greater the acceleration, the greater the bending of the world line in our space-time diagram. Mass, if you've never had a physics course before, is different than weight, even though we tend to use them the same way. Weight is how much Earth is pulling down on an object with gravity, whereas mass is a measure of its inertia. So they're proportional to each other on the surface of Earth. So the greater the weight, the greater the mass, but they're not the same thing, because if I go into deep space, I have the same mass of my body, but I would say my weight is zero because there's no gravitational forces on me anymore. So this is really mass, which is kind of how hard it is to accelerate something. The greater the mass, the lower the acceleration. Newton's third law just says that when one object exerts a force on the other one exerts a force on the one that's equal and opposite. And so that just means if I pull on the door with a certain strength force, it pulls on me in the opposite direction with the same strength force. They exactly balance out that way. Okay. Now, I've just given the briefest possible description of Newton's gravity with no equations whatsoever. But there are some strange coincidences that you've all heard about before, or at least one of them, famous one, that occurs for Newton's description of gravity combined with his laws of motion. Every object, regardless of its mass, follows the same trajectory when acted upon by gravity. And here's a famous example of that. Galileo dropping the different mass objects from the Leaning Tower of Pisa, and the two objects, they've got to be dense enough that air resistance doesn't play a big role. Of course, a feather is not going to work if you compare it to a lead ball. But if you have two fairly dense lead balls, it seems like, well, the one that's really heavy maybe should fall faster, but it doesn't. Its acceleration is exactly the same. And that's, in Newton's theory, that's a very strange coincidence. Why would these things move exactly the same way when they have hugely different masses? And the idea is, yes, there's a bigger gravitational force, but there's also more inertia. Harder to get something moving when it has a big mass, and those two effects cancel each other out. But why is that? That seems like a coincidence. It seems like we're missing something. Why would such a strange coincidence take place? There's a reason for it, according to Einstein. Okay, huge and tiny objects orbit Earth in the same way. That's another manifestation of this, right? If you take a little tiny rock and put it in orbit around the Earth, and a piano, grand piano right next to it, right? A tiny object and a big object, and you start them out in the same way, they'll sit right next to each other, perfectly happily orbiting Earth right next to each other. They won't get any farther away from each other. They're following the same trajectory, even though they have hugely different masses. Well, they would, because they're attracting each other. But in this case, if we're just watching how they follow their trajectory, ignoring the attraction they have to each other, yes, you're right. Technically, there's a tiny bit of acceleration causing them to move together. But that seems like a great coincidence too. Right? Why would something with a huge mass travel along the exact same trajectory? Maybe the better way to say it is, if I set a little rock in motion And then in a separate experiment, I set a grand piano in the same motion initially. They would stay at the same positions for evermore. Second coincidence is that there's no way to shield objects from gravity, and there are from other forces. In other words, there are boxes called Faraday cages where if I have an object inside that's very sensitive to electric fields, no matter what electric charges I put outside this box, the box will magically shield the things from electric forces on the inside. And there's nothing really analogous that you can build for gravity. So that seems like a strange coincidence too. Here are some other signs that Newton's theory of gravity is probably not the final theory of gravity. Leibniz brings this up. The force that Newton describes exerts an action at a distance, or at least Newton didn't know how to repair that at the time he was proposing it. It worked, but it seems to be objectionable. Differences in mass position would be, so in other words, if I imagine a location 20 light years away, there's some big mass over there, and I've got a little mass here, right? And technically, there's still a little bit of attraction, even though they're really far away, they attract each other. And I wiggle my mass here, pull it farther away, and then closer, and then farther away. That's instantaneously communicated with that mass that's farther away. In other words, the force gets bigger and smaller and bigger and smaller, and there's no delay within it. So you can, in principle, communicate instantaneously with any other location in the universe. And we're going to find out, we haven't gotten there yet, that this is like chapters 9 and 10 or 11 and 12 or something like that. This is inconsistent with the result. We're going to find out that no faster than light signals are going to be consistent with special relativity. So Einstein's theory that we're learning about doesn't allow you to instantaneously communicate with someone. If you want to communicate with them, the fastest you can do that is by sending something that goes at the speed of light, or anything slower than that. But there's problems, big problems, logical consistencies that happen if you imagine that you can communicate faster than the speed of light. You can actually travel backwards in time, and then you could kill your grandmother before your mother was born. And then what am I even doing here? How do I explain the whole story of happened leading up to here? All sorts of mayhem breaks loose. You might also think that, if you think of a light pulse or a photon, even though we're not talking about that way in terms of Merman, as being a massless particle, light doesn't have any mass, there is energy associated with it, that it shouldn't be affected by gravity. Gravity is a attraction between mass and mass. And so a light pulse doesn't have any mass, it shouldn't be affected by gravity. But then again, it's not so clear. In other words, if we look at Newton's second law, yes, the force on it is 0, but its inertial mass is also 0, and 0 divided by 0 always means we can't make any definite conclusions about how it should move. So it's, Newton's theory of gravity and motion doesn't really tell us anything about that. I don't know that we're going to have time in this block term to talk about E equals mc squared. I would hope that we could get there, but that's just a hope at this point. But everyone's heard E equals mc squared, that there's something about mass and energy that are equivalent to each other. And in Einstein's theory, having energy is just as good as having mass. And so if you don't have mass, but you have some energy, still you're sort of affected in the way you move the same way. And so by E equals mc squared, it seems like light should be affected by gravity, but Newton doesn't tell us any way to compute how light would be, there's no force on a light beam according to Newton. Yes? Well, the question is, what is a zero gravity machine? I mean, have you ever seen one at a science fair where, that's an honest question. I've never seen a zero gravity machine. Yeah, I mean, there are various ways. People, there's also those things with the big fan where you can pretend you're skydiving, but you're just sitting here on Earth. But yes, there are those things, but they're not really counteracting gravity. What they're doing is putting some other force on you that counteracts the downward force of gravity so that overall you have no force on it when you consider all the forces. So they're not getting rid of gravity, but rather they're counteracting gravity with a different force in the water tank. That's what's called the buoyant force of the water. So one of the fun things about scuba diving, I don't know if anybody ever scuba dives, but it's fun because it's the closest that I've ever felt to being able to fly. In other words, you can go up a rock wall and just keep going up and look around and then decide to go down, and you can adjust your position. It feels like you're flying. So if you have a fantasy of flying, try scuba diving sometime in the ocean. You know, murky lakes in Kentucky aren't so much fun. You just can't see that much stuff. But if you go somewhere with nice clear water, go soon before all the coral reefs are dead. So the point of this whole list here is maybe these are clues. We need to look for a different theory of gravity, and that's where we're heading into now. So let me just, in the last 8 or so minutes of class, set up the idea of how we're going to start to think about the geometry of space-time, how it curves around. That's the point of the rest of what we're going to talk about. According to Newton, space itself has a geometry. We would call that 3D, three-dimensional Euclidean space, right? Just like the plane of the blackboard is a two-dimensional plane according to Euclid, the space we live in as conceived by Newton is this box in which things happen that is a three-dimensional box. And there are straight lines between things, and you can measure distances between points and all that kind of stuff. It's also, we've been seeing in the philosophy class, it's important that it's homogeneous. That causes some problems according to Leibniz, right? Because every point looks like every other point, but that's Newton's conception, is that it's homogeneous. And it's also independent of time. Space now looks exactly the same as it does 3 seconds from now, and so on. In Newton's theory, gravity is merely a force, one of many forces. It behaves just like every other force. It acts on objects which can move around within the container of space. But so the electric force does that too. So does the magnetic force. So it's just one of many forces. In special relativity, space-time has a geometry. It's not just space anymore. Up here we were talking about space. In special relativity, we're talking about space-time. That's our space-time diagram that we were looking at. It has a geometry that's 4-dimensional. Now, this geometry was 2-dimensional because we were imagining people could only move along one line. But we can really move in 3 spatial dimensions, plus there's a time dimension. So we would need a 4-dimensional picture. It's not even easy to draw a 3-dimensional picture. I'd have to build a sculpture. So most of the time, we limit ourselves to 1 spatial dimension and 1 time dimension, just so we can draw it on a page like this. So here is a space-time diagram, which would be 2-dimensional, but the real space-time is 4-dimensional, and there's no good way to draw that. So that's why we, just consider the simple case of things often moving along a line. But it's homogeneous. This point here in space-time, there's no fundamental difference. Once I take away the axes, all these points look the same. There's no edge to it. It just keeps going on forever and ever. It's an infinite plane. Again, in special relativity, gravity is conceived of as merely a force, one of many forces, that acts on objects that can move around within the space. We've said that Newtonian gravity appears to be inconsistent with special relativity because it allows instantaneous action at a distance, and we're going to show that no information or signals can travel faster than the speed of light. If they could, you can travel backwards in time, which causes all sorts of mayhem. The difference with general relativity, which was, I can't remember how many years, but maybe somebody knows how many years between special and general relativity, but it was on the order of 10 years. It took Einstein a long time to develop this more general theory after the special theory. Space-time is not homogeneous. It doesn't look the same everywhere as you move around in there, unlike the picture I just showed for special relativity. Its geometry, the way it curves, changes from point to point in space-time. And perhaps most importantly, gravity is not at all like other forces. It's not like the electric forces and magnetic forces. In fact, you can think of it as not really a force at all. The effects of gravity are just communicated to particles by the curvature of space-time. So if you're going through a region of space-time that's particularly curved, there's no force on you. You just travel in the most natural way. And the effects are the same as if we had gravity. Okay? So our goal for the next day, that means Monday, or maybe day and a half, is to first understand the geometry of space, because it's hard enough just to think about spaces. So we're going to imagine still space as a container, but maybe it's not like the container that Newton is conceiving of, this 3-dimensional box. It could have some other kind of shape. And then later on, we're going to generalize that to the geometry of space-time. Okay? And maybe that's a good place to stop, even though it's about 4 minutes till, just to start with a new topic on Monday. Any questions on that? Jack?
So you said gravity is not a force in the sense that other forces are forces.
Yes.
So
In other words, it's not going to cause lines in space-time to bend. They're going to still be straight. When something is only under the influence of gravity, it's going to be traveling completely straight in space-time, in a curved space-time. And we'll see an example of how that works later on. You have to understand what straight means, but it is literally straight. It's easy to misunderstand how something might, here's a curved space. I'm holding it, for those of you at home, I'm holding up a basketball. If I'm a two-dimensional creature that's moving around in this space, you may think, as I'm going along this line right here, that I'm curving around. We're going to make an argument that you're actually not curving at all. That actually it's going to be completely, this is as straight of a line, and it's not straight at all. It's perfectly straight in the same sense that a line going through our space is straight. It appears to curve because of the way I've embedded this in our three-dimensional space. But if I took the top of this basketball and dimpled it in, you'd say, oh, instead of curving that way, now you're curving up this way. Well, the inhabitants of this two-dimensional space wouldn't have any idea of the difference. It's all the same to them. We'll elaborate more on that on Monday.
Hello, Dr. Kelly.
Yes. Sounds like Muchiri.
Yes. I mean, when you're explaining how forces accelerate things in space, can force also decelerate the speed of things in the world life?
I wasn't sure I understood. So forces can change the directions that things move in space, and they can also change the speed at which they're moving. Was that your question, Muchiri?
Yes, and then you said, from what I understood, it's like you only mentioned they accelerate things. Can they also decelerate things? Or it's only accelerate?
Did you say decelerate, like slow down?
Yes, can they decelerate things? Yes.
Yes, absolutely. So, if two masses attract each other and one of them happens to be moving away, but this one over here is pulling on it, it's going to slow it down till it comes to rest maybe, and then it starts falling back inward. So, yes, acceleration includes both speeding up and slowing down and changing direction. All of those are generically called acceleration.
Oh, okay.
Anything else? All right, if you're still working on those chapter 7 problems, consider staying after today. Muchiri, are we meeting at 11:30 today?
I don't think so.
You don't think so? Okay. Well, then I may still be here then. So feel free to stay on. Those of you on Zoom, I'm going to leave the Zoom channel open if you have homework questions as well on the chapter 7 stuff. If not, have a wonderful weekend, and I'll see you on Monday for more curved spacetime. And Jack is reminding me, please don't leave the room without giving me these rulers back. We can put them right here.